Hello everyone. In this video, we're going to guide you with a tutorial to create a hydraulic actuator model. Our learning objectives in this topic are the following: to be able to create a simple hydraulic system step by step, and to calculate the required parameter values based on system information and objective. By doing this, you will be familiar with components from HYD library, and you can build a system model all by yourselves in the future. Now, let's start with this tutorial. We have an ideal mass staying on the ground, and our objective is to move it horizontally forward and backward. The known information of the parameters of this system is given below, including friction coefficients, the mass value, the required moving displacement, duration limitation, and so on. Besides, it's also mentioned that the actuation is done by hydraulic jack. The pump speed is also defined. With information provided in this slide, now we can start the modeling work with the first step. In first step, sizing, we will first need to set the parameter of translational mass component. From the snapshot on the right-hand side, the mass value, friction coefficients, as well as displacement limit are all well set. Since we're supposed to use a hydraulic actuator to drive the mass, then to overcome the stiction force of 15 Newton with pressure of 5 bar, we need to calculate the required minimum piston diameter. With calculations shown in this slide, we finally get the minimum diameter value of 6.2 mm, and it will be set in the cylinder component. A note here is, we will first set the raw diameter to 0 to simplify the calculation. Then we can create a small circuit model with hydraulic cylinder, translational mass, pressure source, and tank. Also, don't forget the orifices with diameter of 4 mm. They're used at inlet and outlet ports of hydraulic cylinder. After a simulation run, from the results shown in the middle figure, the mass can reach 0.5 meters around 3.5 seconds. But it didn't fulfill the maximum duration of 2 seconds. So, we need to increase the diameter and check if we can speed up the movement. After increasing of 30% of diameter, namely 6.2 mm multiplied 1.3, with this updated diameter, we can see from the right figure, the mass displacement can reach 0.5 meter within 2 seconds. In the second step, the system requirement is updated. The pressure source needs to apply in different chamber for different phases. To meet this requirement, we will use a 4-way 3-position valve. From this valve icon appearance, you can already understand that flow passages can be switched between left and right position. By imposing input signal of 40 mA or minus 40 mA, the valve's position will be changed to realize switch between flow passages. Under pressure drop characteristics parameters, we will need to change the characteristic flow rate at maximum opening to 10 liters per minute for all flow passages. Then at third step, we can try to add this 4-way 3-position valve into the circuit. Besides, in actual system, we have a raw diameter of 3 mm, then it means we need to increase the piston diameter accordingly to compensate. You can try with different piston diameter values and check the simulation results. With diameter of 9 mm, we can still meet the duration constraints. Also, due to causality, there will be pipe components between orifices and valve. Please set their diameter and length with provided parameters. From the displacement plot, we can see the mass component moves both forwards and backwards with different imposed input signal. During first step, we need to consider in real system there is no ideal pressure source but pump, so we will use an ideal fixed displacement pump instead of pressure source. To size the pump, the system flow rate is to be considered, as we know the flow rate equals to pump speed multiplied the pump displacement. From the simulation results, we can observe that maximum flow rate is around 2 liters per minute. With the given pump speed, 500 rpm, what is the required pump displacement theoretically? And usually, we need to add a security margin to ensure the pump capacity can meet the system requirement. So, a 15% of security margin is to be added, and let's check the calculation. The theoretical pump displacement can be calculated with maximum flow rate and pump speed at 500. It's 4 ml per revolution. Then with a security margin of 15%, the displacement is to be increased to 4.6 milliliter per revolution. We will select an ideal fixed displacement pump and set the parameter as shown on the snapshot. After performing a simulation run and from the results, we see a strange behavior of mass displacement. What's happening? It's because there is no pressure regulation in the system. The pump keeps supplying flow rate into the chamber, even when it is not needed. The consequence is the chamber pressure becomes very high, see below the plot, which is not realistic. So we will need a pressure relief valve to limit the system pressure. At the beginning of this tutorial, we set the pressure source at 5 bar. Now we can add a parallel flow branch of a relief valve to the pump and set the cracking pressure at 5 bar. Once the pump outlet pressure is higher than 5 bar, this valve will be open or activated, so the excessive flow will be flowing through this branch into the tank. Now we can see the results on top right. The mass displacement curve is same as before. Except for cracking pressure, there is another parameter called relief valve flow rate pressure gradient. What's the meaning of this parameter and how it will impact the valve behavior? We can first set a batch run with different values of this gradient. From the left figure, we see from 3 different gradient values, 550 and 10 liter per minute per bar. The pressure in the left chamber are maintained at different level, and only the red curve corresponds to 500 liter per minute per bar is the closest to 5 bar. It's because the relief valve has to have a capability to release the unnecessary flow. Otherwise, if it's too restrictive, the pressure cannot be maintained at desired level, but at higher level. Besides, for different pump displacement, we can observe also that low pressure peak can appear if the pump displacement is not enough. Finally, if we can have more information about the pump or any other component in this hydraulic circuit, we could select a more complex submodel to perform a deeper or more detailed simulation analysis. For example, we can switch the pump submodel from an ideal fixed displacement one to a component required tabulated efficiency. Then the pump model can take into account the volumetric efficiency or leakage. Okay, that's all for this short tutorial. Let's summarize what we've learned from this short lesson. You have learned how to create a hydraulic system model with fundamental components from HYD library. You should be able to calculate the required parameter value for each component to reach the system performance criteria. With this, we end our lesson on hydraulic actuator. Thanks.